A GFG question that we are going to discuss today is consecutive ones not allowed. In this question, we will be given an integer n and we need to count all the possible distinct binary strings of that length such that there are no consecutive ones. Let's understand this problem. So to understand this, we will be using example. For that, let's say n is equals to 3. So that what is expected? We need to return the number of binary string, valid binary string, such that there are those binary string does not have any consecutive one. Like as in this example, we can see these the strings here all are of length 3 and none of them have consecutive ones. This is what expected uh, from us in this question. We need to return the number of those binary strings. For that, let's understand this a bit more clearly. Let's suppose here we are given like for a string there are three indices as the length is n. So what is expected is let's suppose if we are placing 0 here, if we are placing 0 here, we can place 0 here, we can place 0 here, we can even place 1. The binary string is what, either it contains 0 or it contains 1. But the main logic to solve this question is if the very last index has 0, then place the new element that we can place depends on what was there in the last index. If it has 0, then we have got the freedom to either insert 0 or 1 because it does not violate the valid binary string condition, that is the binary string should not contain any consecutive one. If if we go to place 1 when our last inserted element was also 1, then it violates the condition, so we need to avoid it. So the condition that we need to keep in mind is if the last element was 0, we can either we can we are we have got the freedom to choose 0 and 1. But if we have 1 at our last index, we are constrained to choose only 0 as our next element. For that, let's understand this with a tree. We are given, let's suppose we have first started with an empty string, and these are the indices we are going to fill for the string. Like we are first for the 0th index, what we are going to do is either we will start with first by placing 1 or by 0. It's up to us, and it's valid to choose to start for both. Let's suppose we are starting with 1. Then the next element, that is the element at the 1 index, we are bound to choose to insert 0 only. But here in the same case, when we have inserted 0 at our 0th index, then for the index number 1 we have the freedom to either insert 0 or insert 1. Similarly, in this case, as the last element was 0, we have the freedom to either insert 0 or 1. But here we can see that the last element was 1, we are bound to just insert 0. And as the last element was 0 here, we have the freedom to choose 0 and 1 both. This can easily be done using recursion. Using recursion, we can just form all the binary string of length n and then calculate how many times these binary strings were created following the condition. For that, the simple code would be this much. We will be starting with a count variable cnt and assigning it to 0. Then we will create a string of length n where initially all the elements are 0. then as all the elements are initially 0, this is the condition where the first element is also 0. Now we are calling this function. What this function will do, it will be having index, it will be having n, which is storing the length of the string and the string itself. It will try to insert, it will, for an index number I, like 0 1 2, we will be starting with 1 to choose what was there in its previous index. If it is if the previous index has one value as 1, then for the present index what we're going to do is we going to simply insert 0 and call the function for the next index. But if our previous if our if the element at the previous index was 0, then we are going to insert 1 and 0 both and calling individually the function for the next index. This is what here the code is doing. It is checking was the past index has the value 0. If it has the value 0, it is calling for 1, and obviously it's after the if, so is always this part is always getting called. But if I minus 1, that is the past index, has the value 1, then it is bound to assign 0 at the current index and will gonna call for the next I plus 1 index. This way we can get all the count, as when I reaches to n, we are updating count by 1, and this way finally when we have called the function for by assigning 1 also at the 0th index and then calling it again, the value at the count variable has the total number of valid binary string, having none of the binary string any consecutive ones. This is a good approach, but there is a flaw in it, as at each of the level what this approach is doing is it is opening two possibilities, and for n indices the time complexity would be 2 to the power n. It is acceptable for smaller values of n, but for larger value of n as given in the constraint 1, the n value can range from 1 to 44, as 44 2 to the power 44 will be a very big number. So we need to keep it in mind and try to find how we can solve this optimally. Like, see, what is expected from us is not to create those binary string. What is expected from us to return the count of all the valid binary strings. So let's find a pattern here to get the insight. See, when you are working here when we are working here when we are working at each of the level, for 0th index, for 1 index, and for the 2 index, what we are doing is for each index we are either inserting 1 and 0, 1 or 0. Here, see at this example, like here what we are doing is the current index value is 1, the current index value is 1, that is this. See, the current index value is 1, and also here the current index value is 1. In both of the cases we can see that the last element, that is the element at the element at the index 1 is 0, and they have the count, the number of binary string as 2. number of valid binary string as 2. Let me explain it further. This will get clear when we only gonna look at this part. See, this part, when the last index, after assigning 0 at one index, for the index number 2, we are getting these binary strings, valid binary string, 0 1 0 0. Here also 0 1 and 0 0. So it's insightful, and we can see that we are just creating this part. We are creating this part again when we are choosing 0 at the index 1. So so the approach is to track how many valid binary string has been created. How many valid binary string has been created by choosing a value 0 or 1 at a particular index. Let's suppose for the index number 2, what we had at the parent index, when the parent value will be, for that storing, we will be using obviously dynamic programming approach, memorization, to memorize the findings at a particular index, so that we don't need to calculate the same thing again and again. We can use the result of previously calculated. For that we will be creating a 2D array vector and assigning. Why 2D? So that we can track what are the number of valid binary string for that particular index when we have chosen 0 or 1. Like here in example we have found that for index 1, the number of valid binary string when we have placed 1, when we have placed 0 at the index 1, was found to be 2. But when we have 1 at the index 1, we have only one valid binary string, that is 1. We are trying to store this much. See, for index 0, when we are at index 0, obviously it will be only one possibility. The value here can be determined only when we are clear about what was there in 1. See, if we had 0, if we had if we had 0 at the index number 1, then for second index, what we're gonna have is, we have two possibilities. We have two possibilities. But if we had 1 at the index 1, we have only one possibility. Similarly, when we are calculating for the index number 1, it will be determined by whether our past index, that is at index I minus 1, here in case at the index is equals to 0, what was there. If if at the index 1 we had, if at the index 0 we had 1, then we have only, we can only assign 0 at our current index. We will be having, so we will be having 2 plus 1 3. No, it's not the case. See, when we had 1 at our 0th index, what we only have is this 0 value, the values, the number of valid binary string coming from this part of the tree. But when we had 0 at our index number 1, we have two possibilities. One coming from what happened when we are assigning 0 at our current index, and what is happening when we are assigning 1 at our current index. That is, when we have used 0, we will be having 3. It will be the sum of 2 plus 1. 2 plus 1. But when we have assigned 1, we had only two valid binary string, these two only. Now at 0, we have to calculate it individually, as we don't have any past elements for index 0. Let's go and understand through the code part. This is the code part. For if given n is equals to 1, we have only two valid binary string, 0 and 1. We are assigning our dp, we are creating our string. First we are calling when 0 is at the 0th index, and then we are calling the function again when we are placing 1 at the 0th index. In the solve function part, we are seeing that when our index have reached to n minus 1, we are checking whether if the past index has 1, we will be returning 1 0. It depicts that if it has 1, then number of valid binary string getting is 1 comma 0. But if it was 0, then we are getting 1 1. That is, we can place both 0 and 1. Here 1 0 means we can place 1, we can place 0 but not 1. Here 1 1 means we can place both. This is just a part. If we have found the result earlier, we can return that. And similarly, this part is working as discussed earlier. So this approach is a successful approach with efficient time. Thank you.